Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
So more about projectile motion. So another big concept before we dive into the problems. So first of all, as we talked about in the previous segment, is projectile motion, the motion is parabolic. So it's important to understand that this is parabolic. And it's important to understand that the Vx, all right, it doesn't change. So if I've got something traveling left to right as I'm drawing it here, this Vx is always the same. If I launch it with a particular speed, it's going to remain constant. But Vy changes because Vy is fighting the acceleration of gravity, which you call is 9.81 meters per second squared. And so that's the key thing to understand as we do these types of problems. So if we think about launching something, so let's say you're trying to hit something. Maybe you're a golfer and you want to hit a target. Drop my pen. Depending on, you can shoot it off at different angles, right? You can shoot it at a steep angle, boom. Or you can shoot it off at a different angle. And some of this has to do with the speed at which you launch it. Or you can shoot it off at another angle. And actually, let me draw this one further. If these are all the same velocity, you know, what angle is going to be optimal for distance? But maybe you're trying to actually hit a target that's X meters away. And what you want to do is like, I want to hit it, so what angle and what speed should I hit it at? That becomes the question. So if you're golfing, I mean, I want to hit the hole or the green or whatever, and I want to figure out what the angles are to make this work. So this is the idea. Now, something we haven't really talked about, assuming the same velocity, we could prove this mathematically, but it turns out if you want to get the maximum distance, you know what this angle needs to be? 45 degrees. So if you want to get it the furthest possible distance, the correct angle, if you will, is 45 degrees. That's pretty steep. Boom. You know, half of 90. That's going to be your biggest distance. But let's label some things. This is kind of an important graph, or to draw. So let's just make sure we understand what each of these means. Here I'm going to launch something a long ways, but let's label this, because if we label this, well, this will make life so easier. So right here, if you will, from here I'm launching it at this, and this here is the launch angle, or theta, right? So let's call that the launch angle. And we've got, in this direction, the Vx, and in this direction, the Vy. And we're going to figure that out using sines, cosines, and tangents. Right? And as a side note, this is Vx. Vx is the same here. It's going to be the same here. It's going to be the same everywhere. Okay? Another really important point is that the tip of the parabola, this is where Vy is equal to 0. That's going to be very important because it helps solve so many of these problems. And also another important point about this point is this is 1/2 of the distance. And by the way, this is the distance from here to here is the distance, right? But this right here is half the distance, and that's important to figure things out because like half the distance, half the time. So it's also half the time. So let's talk about the time. Time's interesting thing is that time's a great way to connect. So time connects distance to velocity, because time is it doesn't change. It's the, think of it as the connector when you're solving these problems. That's how you can connect. It transcends directions, and you can use it to go between the vertical. That's the way to say this. This is how you can go between the vertical plus the horizontal. So time will get you in both directions when we start playing with the equations. A couple more things. This is dx. And at some points, you're going to also want to find out what dy is. right? How high does the ball go as I hit it with the golf club? So there's dy, there's dx, and there's vx, vy, but then time is the one that'll get you to convert between one and the other. So that's sort of the big picture, so you understand what all the variables are. And lastly, let me say this. I think a way to really kind of keep track of all this is to create a table. You've kind of got x's and you got y's, and try and figure out what's what. You've got distance and distance, dx and dy, and you've got vx and vy, and actually you've got ax and ay sometimes, although it's much more common to have an ay and not have an ax, because that's going to be the acceleration of gravity and projectile motion. And then you've got time, and time is usually the same number. These are almost going to always be equal. And what you can do is you can just like plug in your numbers. So we're going to try this when we do some of our problems. And then you say, which one do I know? Which one do I not know? Actually, let me talk about a couple other ones. Vx, there's actually Vx, V initial x, and sometimes there'll be a V final x, right? So making a chart of all your knowns, and then what I would do is say equals on both sides, and then you'll say, oh, I'm trying to find time, or I'm trying to find distance. So circle the one you're looking for, put a question mark next to it, and then write the numbers that you know, and then it will make the problems easier to solve when we do that. Next up, we're going to solve several different types of projectile motion problems, and there are like quite a few types, and we'll work through them one at a time. See you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.